Okay, so I'm going to make this video because one of my friends and clients made a video and was answering some questions about the product, the Neuma 4, on reading from the website, and it made me think that there is an opportunity that I can use to explain some of the things in deeper detail. So that's what I intend to do here. Okay, so a lot of it was already explained pretty well. So really I just want to go over some of the stuff that was a little bit more complicated. So I will start. So I'll start with, okay, the specifications of the machine. On the website, you'll notice it says 26 millimeter, 29 millimeter, 27 millimeter. That's all for the one grip, the standard grip. 26 millimeters is at the point where it's closest to the needle cartridge. 29 is at the fattest point in the middle of the grip, and 27 is at the back or top of the machine where you're making adjustment. The length is 88 millimeters. That's from the cartridge receptacle all the way back to the the highest point, which would be the top of the adjustment knob. So the actual grip itself is about 79 millimeters, which is the bulk of what you'll be handling. Says weight is 122 grams. There is some variation, and to be totally honest, I'm not entirely sure what that is. I have weighed them multiple times and noticed that they vary. So I've seen them as low as 115 grams and as high as 122. So I put 122 because that's the worst case scenario. Output 8.5 watts, that's the motor. The actual torque rating is 6.8 Newton meters. As a direct drive, and then at the moment it's 3.6 millimeter and 2.75 millimeter cam options. Okay, so here I've got listed problems and solutions that I have noticed with rotary machines, and how they can be addressed. So I'll go over those really quick. So here we got a rotary machine with the standard waveform will cause a needle to dwell inside the skin during a stroke cycle substantially. So that's the part where I think I should spend some time sort of illustrating what I'm talking about there. And so let me see if I can find something round to represent a cam. Okay. Okay, so I'm going to use this roll of tape because it's round and it's right here on my desk. Okay, so what I'm talking about with the dwell is actually a lot simpler than it sounds. So if this is your cam and it's driving a needle pusher or a needle bar, what's happening is at some point on this wheel, there will be an attachment point for either the pusher or the needle bar. And so, as you know, this is obvious to most of you. You guys know how this stuff works. So this is moving around, it's on this side, it's pushing the needle in, and then as it moves back this way, the needle's coming out. Simple. So the problem with that is that from about here to about here, and from about here to about here, because we're limiting the movement in this direction, while it's crossing over, we'll call that from 10 to 2, or actually in this case we'll say that is, looking at your perspective, it's actually like, what, 5 to 10, 11, something like that, doesn't matter. From this point to this point, nothing is really happening. You know, a very small amount of forward backward movement is occurring in that section. Whereas from this point to this point, this much forward backward movement is occurring. Hey, cut it out. My dog playing. So the majority of the plunging of the needle is happening here and here. And right here, hang on one second. No, no, go lay down. From here to here, you've got the dwell. That's where the dwell is happening. It's also happening back here, but that doesn't, that's where the needle is in the retracted position. It's not affecting the tattooing. But right here, your needle goes out and then it stays there for a second, not a second, but a portion of the cycle, and then it comes back in, and then it stays there for a second, and then it goes in, and then it stays, and then it comes out, and so forth. So during this segment of the cycle, you've got the dwell, and that's a problem because, you know, if we were just tattooing and not moving our hand, it wouldn't be a problem. How long the needle spends in the skin, it's just making a hole, it's not a big deal. But because we're moving our hand across the skin, the needle needs to get out quickly so that you can continue moving forward. And that's why people comment that they can make lines with a rotary, but they have to slow down their hand speed. That is the reason why, because the needle is not coming out quick enough to move your hand forward at the pace that you're used to without pulling on the skin. So if you were to picture that, because we're not tattooing straight up and down, or we're also not tattooing at this angle, which might solve that problem also. But by tattooing at this angle, which majority of us are doing, if you were to picture the needle not coming out quick enough before you move forward and so forth, you're basically be like kind of plucking on the skin there, or catching it, or dragging, and maybe ripping and tearing, causing more trauma to the skin. So first of all, that causes additional trauma, which, as we can all attest to, more trauma equals worse healing. Worse healing equals not only scarring, but less saturation. The tattoo comes back not looking as good. Also, I don't know if you guys have ever watched, I don't know if I should name anybody on this video, but I've seen an artist who did tests with single needles. Basically, he poked himself, and then he put ink around the needle, and then pulled the ink out, or pulled the needle out, wiped away the excess ink, and there was a dot. Then he poked himself with the needle, did the same thing, put a pool of ink around the needle, then washed it off before removing the needle until it was all gone, then removed the needle and there was no dot. And so what that is telling us is that it's not that the needle is driving and pushing ink in, it's that the needle is creating a hole in the skin. And because there's also a pool of ink, then that hole, once the needle is removed, it's going to close, which creates a vacuum and pulls the ink in. So the reason that I'm bringing all this up is because if your needle is not being pulled out quick enough by your machine, and you're dragging or catching and causing more trauma in that way, you're not only causing more trauma, but you're potentially causing tearing. And a tear in skin is not going to act in that same way as a hole in the skin might. Whereas the hole creates this vacuum and pulls ink in, the tear doesn't create that same vacuum. It doesn't have that pulling effect that a hole would. And so not only are you causing more tissue damage, but you're also pulling less ink in to create solid lines, solid, dots, basically. So I'm hoping that I have completely explained that. So, okay, so the reason that I'm bringing all that up is because that's the primary focus of the Neuma 4 is to address this whole cam situation and this dwell. So as you can see, that there really isn't a way to escape that with a circular cam. There are ways to reduce it but it's very minimal with the traditional cam and follower layout, or the relationship between the cam and the follower. So what Neuma does is it's not using the same type of cam mechanism where the needle has to follow this curve. It does still have to follow a curve, but that's what we're talking about when we say the waveform. So let me find one of these. So what you're seeing here, this is actually an experimental one, but the needle is being pushed by this wave here. And so what I've done here, rather than your traditional thing where you got a attachment point and it has to go and it has to do this part of the cycle in order to start coming back. What I've done here is also, okay, so what I've done is, let me back up 1 second. Because the hesitation or the dwell it's unavoidable in a cam-driven machine. You cannot remove it, but all you can do is you can position it. You can choose to position it in whatever portion of the cam that you decide. So that's the whole idea behind this thing, is to move the dwell from the extended portion of the cycle. In other words, where you're pushing the needle, where you're extending the needle out. We're moving that dwell to the retracted position as much as possible. You cannot remove it entirely, but quite a bit it has been removed. So you'll see on this that on roughly half of the cycle, this half over here that doesn't have the bump, it's flat. And the reason for that is that's the retracted position. So the needle comes back, it stays retracted, and then as this is rotating, it's pushing the needle forward and then pulling it back. But because half of the cycle, it's spent in the retracted position doing nothing, it reduces the amount of in and out by at least 50%. So when a normal cam would dictate that a needle spends, say, 35–40% of its cycle fully extended, which would mean interacting with the skin. If you were to have a 50% flat spot, now you've reduced that by 50%. So if it was 40%, now it's 20%. If it was 35, now it's 17.5. So that's what we're able to achieve. And the reason I say 40, 35, 45, it really is varied. It depends on how deep you tattoo. It depends on really the artist will determine exactly how much. But it's fair to say that it's somewhere between 35 and 50. And that depends on whether or not it's a direct drive or if it has cushion. If it has cushion, it creates an even bigger problem. So here we are back at the cam. So this is representing a cam without any cushion. And the cam itself in a cushioned machine doesn't actually have cushion in the cam. The cushion exists somewhere between the cam and the needle. However, it's the same. So if you were to put cushion in a traditional rotary style design, what you are effectively doing, if this is the poking and this is the retracted position, retracted, extended, you're putting a flat spot here on the forwardmost position of the cam. That's where the needle is interacting with the skin, where the skin is pushing back. And so if this was flexible, you would see as I pushed here, that circle would flatten out and create this round on this side and then flat on this side. And so I'm gonna ask you to use your imagination for a second. So let's say you tattoo at a depth of, if this position is the furthermost extended, and say a little bit back is about how deep it'll go, right? Then you still need to make the same depth of puncture in order to make the tattoo effectively saturate, right? So if this is flattening out, now your depth is going to be somewhere back here. Let's say the gap there is is illustrating how deep you are with a standard no-give machine. So now if the skin is pushing back, flattening this out to roughly that same line, then your depth is going to be roughly there. So rather than the dwell occurring from here to here, it now occurs from here to here, which, as you can see, the distance from here to here is longer than the distance from here to here. And so when I say it's extending the hesitation for each of the cycle by adding give, that's what I'm talking about. Instead of being this duration of time, it's this duration of time. And that's rough. And again, it depends on how deep a tattooer likes to tattoo and a number of factors, including like exactly how much give is there. Some people like to have a lot of give. So on a rotary, the more give, the worse. The more give that's happening, the flatter that flat spot becomes, the wider that flat spot becomes. So if you like this much give, you know, you're extending your cycle by that much, versus if you like the entire, you know, maximum amount of give, you're extending your cycle even more. It can be up to like 50% of the actual cycle timing it's spending, not quite 50, but close, is spending, the needle is spending inside the skin, which, you know, will require you to really slow down, or it can cause damage. So if you're a proficient tattooer, you know that you can't do this with a machine when you're feeling a lot of feedback on the skin. So they slow down and they do their lines really slow, or they build them up. I've been doing that for years. However, if the needle's getting in and out much quicker, then you can move your hand much quicker. And that's why when you have a lot of artists who use a rotary for, let's say, the bulk of their work. However, they prefer to use a coil to do their line work, and that would be why, because a coil is getting in and out of the skin really quickly, so it doesn't have this same kind of a profile. So if you were to map this, you basically split the circle in half this way, and so if you're looking at the waveform, so up and down on our, I'm going to do it in reverse, so up and down here would be representing needle position, so we'll do it this way, poking, and then left to right is representing time. So if you're mapping that, it's needle goes down, needle goes up, needle goes down, and that's over time. So on a rotary machine, if you would just take this cam, cut it in half, then your waveform looks like half circle, half circle, half circle, half circle, roughly, and they call that a sinusoidal waveform. If you were to map a coil's stroke profile, it looks a lot like this. So you have this really sharp, so okay, back here we're representing, I'm going to do it in reverse, so it's going to be more like this. So here, the needle is in the back position. So as it's coming down to poke, it's building up speed. It's under the most amount of spring tension here, sorry, the least amount of spring tension here, so it accelerates really quickly until it gets to the poke. Then it's under the most amount of spring tension here, the power is removed, and so it's being removed very quickly as well. It's accelerating a little bit quicker than it's retracting. But the amount of time, if you're only poking this deep, the amount of time spent in the skin is very small. It's 10% of the entire cycle length. The only downside to a coil that I've noticed in terms of stroke profile is that a lot of times when it hits the coil and turns off, there's a little bit of a vibration, a little bit of a hesitation here, where it kind of acts a little bit funny right in that area. It's not perfectly clean line there. It's clean to this point, and then it's a little funny, and then it retracts. But because it's so quick, it's still far superior to a rotary. And I would say potentially any rotary, for that simple reason that it gets the needle in and out very quickly. So the Neuma 4, it can't quite get to a 10% as far as I can see at this point, and get very close. Like I was saying earlier, it's roughly 17.5% is about the closest I've seen it so far, without causing a lot of radial forces on the the motor shaft, which is the main factor which will deteriorate a motor. So yeah, I could probably push it farther than that, but it would come at the cost of the motor's lifetime. And so it's important, obviously, to have a motor that lasts really long. I would say a minimum of a few years. So, you know, my school of thinking is the motor is, you know, if you see somebody turning these things up to 9 volts, which is the max, actually you could turn it up beyond that, but for extended periods of time, I would not recommend it. And honestly, I would not recommend even using 9 volts, because at that voltage, it's going really, really fast and very, very powerful. And the reason that using such a powerful motor is because my thinking is that you're better off using less of the overall output than using all of the overall output, or even like pushing it beyond that. There are some tattoo machines out there that are 12 volt rated motors, and the manufacturers are saying go ahead and run it to 14, but that most times will result in a short lifespan for that tattoo machine. It might be 9 months, it might be a year, or something like that. Whereas if you're using a 6 volt motor, and a 9 volt motor, and you're never really going above, say, 8, which I would say is the case for the Neuma 4. I've heard some people try to use more than 8 just to experiment and see how fast they can tattoo, because the efficiency on these is really great. But as a general rule, I would say no one's going to use more than 7 point something. 7.7 is like really moving really quick. So you're never pushing the motor to its limit. So the motor will last a long time. Okay, and so I think that explains that. To anticipate some questions, are there any other tattoo machines out there that are manipulating the stroke profile or the waveform? And the answer is not that I'm aware of. I think that it's all pretty straightforward as far as the cam and follower relationship goes. Okay, so the typical cam and follower relationship layout. Well, let me just say that, so the typical cam and follower layout limits the amount of variation that can be done to a stroke profile or waveform. So, by the way, waveform is the technical scientific definition or word, and stroke profile is just something that has been coined based on the specific application of tattooing. And so one thing I wanted to really quick mention, people ask me a lot why I chose the stroke lengths that I chose, and will I make longer ones? So I'm gonna come back to this thing. I think, okay, so first of all, to answer the question very simply, the longer the stroke length, no matter what type of rotary machine we're talking about, the longer the stroke length, the bigger the radial force will be on the shaft. So if this is your motor shaft, it spins, and you've got a cam spinning around it, right? If a cam is, if there's a lot of forces going this way on your shaft, it is stressing the bearings that are holding it in place. The bearings is the main feature within a tattoo machine that is determining the lifespan of a tattoo machine or its motor. When those bearings are worn, the motor is done. I'm not sure if you can replace bearings. To be totally honest, I think you probably can. But the the amount of work that needs to go into it, I think you might just be better off replacing the motor at that point. And I could be wrong. But point being that the least amount of radial force that you can apply, the better. So by having a much bigger stroke profile, you add the offset. So the longer the offset is from the center point of the shaft, that determines your stroke length. So let's say if here your stroke is 1 millimeter, 2, 3, 4, 5, and so on. So the further offset you become, the more radial forces you're putting on the motor. And so with something, let's say I put a 10 millimeter stroke, which is an exaggeration, or let's say 6 millimeter stroke, something really, really long. It's a lot of radial forces that are being applied to the shaft, which is going to reduce the lifespan of the machine. So the reason that I have chosen 3.6 and smaller is that you're likely to have a much longer lifespan for your tattoo machine. And I am experimenting with longer because I would like to know what is the actual max amount that I can push that while maintaining a long lifespan of the machine. If I can get away with 4.2 or something like that, I absolutely will. However, one thing I also want to illustrate is that the reason that most people are asking for a long stroke length on a rotary is that they think that it lines better. And in a traditional rotary layout, it's true. 5 millimeters of stroke on a traditional rotary will line better, and I'll explain why. Because, coming from a coil background, that's reverse of what we would have said, and our current coil user would probably still say a short stroke is better for lining. Reason being that it's quick, it takes less time for the needle to do its cycle, and it's really snappy. It gets in and out really quick. So 5 millimeters of stroke. If we were to picture this being, let's say your motor shaft is here, and the distance from the center of the motor shaft to the center of the attachment point on for the needle bar is 5 millimeters. That would determine that this has a 5 millimeter. Well, no. Actually, no. So the furthest distance, so here, this attachment point being here versus this attachment point being here, the distance there is 5 millimeters. That determines that this moves 5 millimeters, right? So the reason why that being that long, it appears to line better. Some people think that it's because of the ink flow and that kind of thing, or just having your needle hang out farther, something like that. But so let's say that you're gonna. So if this is 5 millimeters of width right here, and let's say you're going to tattoo. Actually, let me start over. Let's say this is 2 millimeters. So we're talking about a 2 millimeter stroke, right? And let's say you're going to tattoo 1 millimeter deep into the skin. Okay. So that would mean that your interaction portion would be in this section of the cycle. And this is exaggeration for a purpose. And I'll get to that in a second. So this distance is 1 millimeter. That's the portion that you're tattooing. Okay, so as it's coming around this part, it's not doing anything. As soon as it hits here, you're starting to interact with the skin. You're still interacting with the skin until you get to here, and then not. Okay, so the amount of time it takes to get from here to here is the same amount of time as it takes to get from here to here, right? This side or this side, same thing. So let's say it's a second, half a second back, half a second in, right? So now let's pretend this is a 5 millimeters stroke, okay? But you're still only tattooing 1 millimeter because we're not gonna suddenly tattoo 2.5 millimeters because we have a 5 millimeter stroke. So now we divide this into fifths. So let's say it's like 1, 2, wait, 1, 2, 3, 4, and 5, something like that. Bear with me. Okay, so basically, you're only tattooing, you're only interacting with the skin in this section right here. Same, that's 1 millimeter. So that means the amount of time it takes to get, for the needle, for the cam, excuse me, to get from here all the way back around to here until it's interacting with the skin again is much longer than it was in our first example where it only had to go from here to here, right? So now what we've done is we've added this amount of time here and this amount of time here that the needle is not in the skin. So the dwell is reduced. So now the needle's only spending this portion of the cycle in the skin and spending this portion of the cycle outside the skin, which reduces this dwell rather than it being from here to here or from here to here. It reduces that quite a bit. And so it's effectively doing what the Neuma 4 is doing, in that it gets the needle in and out quicker comparatively to the rest of the cycle. So that's why it feels like it's lining really well. Now the downside, because I mean, reality is if there were no downside, then there's no difference. And so there you go. Like it's the same, right? However, the fact that we're putting the radial forces on the shaft of the motor, we're increasing that by quite a bit by putting the offset, I believe it was 2.5 millimeters, since this is the 5 millimeters. We're putting the offset further away from the shaft, which puts more radial forces on the shaft, which will reduce the lifespan of the motor, which reduces the lifespan of the unit as a whole. So first of all, the less of an offset, the longer the lifespan of the motor, the longer the lifespan of the tattoo machine. Also, because we're able to achieve that speed and recoil, you know, the action of the needle going in and out of the skin quicker in relation to the rest of the cycle, without using 5 millimeters of stroke, you're going to get a very effective lining experience with this type of a cam, for that exact same reason as I was just illustrating with a long stroke, without having the long stroke. So you're going to get that really hard hit and that really quick recoil without putting a bunch of stress on your motor. It'll last a lot longer. And so that's why I've chosen that 3.6 and even smaller. If you can stand to get away with a shorter stroke, your motor will last longer, and I recommend it. If you're only using, if you have a 3.6 millimeter stroke and you're only using, let's say, 2 millimeters of it, all you're really doing is shortening the lifespan of the motor. Whereas we can manipulate the cam to get the same effect without having to shorten the lifespan of the motor. Okay, sorry, some of that was probably redundant, and I apologize for that. So we talked about the cushion, we talked about waveform. Yeah, so the modern pen style stuff, what I'm talking about as far as ergonomics goes, is that they keep getting fatter and fatter and fatter, and that's to allow for, you know, most of the skinny ones are using a swash plate, which is not what this is using. This is using, it's using one of these, you know, which is bobbing up and down, and that little ramp is being driven by a bearing, versus a swash plate, which literally does this wobbling thing, which pushes a pin, and the pin pushes a carriage, and the carriage pushes the plunger. So there's less moving parts, like quite a few less. And but you're still able to get away with a narrower pen arrangement, because like with the fatter ones, they're eliminating the swash plate by they're using a regular, like a standard angled arrangement. So if you picture traditional rotaries, which the motor is here and your tube is here, you have this perpendicular effect happening. And that's what's happening in some of these modern pens that are really fat. They just have a really small, flat motor, but it still has that perpendicular effect happening inside the motor. They have a bent pusher. The downside to that is that, first of all, the ergonomics, it's really fat and there's no way to get skinnier. So some people prefer fat, and that's okay. I can grow the size of my grip without changing the internals. They can't shrink the size of that grip because the motor is already as small as it can get to fit in that space because it's perpendicular. Mine is parallel, so that's why I can get away with using a smaller. And I could technically even get smaller than that if I wanted to reduce the power. I don't particularly want to, but we'll see if there is a need for that at some point. The other downside to the perpendicular, traditional angled rotary inside a tube effect, another downside to that would be that the motor, being as small as it is, it lacks power. So I think that some of them are like 3.5 watts versus the 8.5 that I'm using. So it's quite a big difference in terms of power. So having a skinnier machine that will put out a lot more power to me is preferable than to have a fat machine that can't get skinnier. That in order to grow the power, you would have to grow the diameter of the machine like quite a bit. Okay. I also, this is self-explanatory. So then there's the ease of switching up cams. This is I don't actually offer this particular one because I polished these just to see what it would be like. Downside is it makes it slippery. You can't really grip it so easily, but it looks nice. Change cam on this is really, really simple. There's the cam, you take it out, you grab another cam, you put it in, you're done. No tools required. I'm gonna take that out because this is actually an experimental one and this one is not, but yeah. Very simply done, no tools required, no tools ever gonna be required on this machine. Oh, and then there's the whole bagging grip and all of that. So the way that I do this, I'll show you, is there are a couple ways you can bag this machine. One way is you put your RCA on there. Straight RCA is best, so you don't have to correct it after you've made your adjustment here. You bag your RCA with a clipcord sleeve, and then tape your bag to this adjustment knob. This is just the tape I have laying here. Use whatever tape is appropriate. So now you've got the bag taped here, and then you can put another bag over this machine so they're independent of one another, and you can turn that to adjust the depth or the throw and not affect the bagging of this. And so that way you don't have to turn within the bag, which is a little bit of a pain. Another way to do it, open the machine, there's two grommets here, pull this grommet back, put your bag underneath that grommet, put it back in the groove. So now your bag goes inside this little gap here between the inner and outer housings, the grip and the inner housing. And that will, eliminate any potential for anything happening to this section of the machine. And when I say you don't need to use a bag, that's because this is autoclavable and or cold sterilizable in its entirety. So even if you were to tattoo this bare, you could autoclave it and it would be sterile after that. A lot of people like to bag it anyway because it makes their job a little bit easier when it comes time to clean. If you get ink all over it, it's a pain in the butt to get it off. But that would be, you know, I guess it also would further control the contamination potential by bagging that. Okay, so back to this. I think I've probably already covered all this. Okay, so one last thing I would like to address is this last statement here. It says oversized grips are available if preferred but not necessary. And I do know that some people prefer an oversized grip, and I have my opinion on that, and I'm realizing that a lot of it is just preference, and so this may or may not apply to you. To me, the size of this, smaller would be better. When I draw with a pencil, I draw with a regular pencil. I don't bulk it up with Scentsy wrap or anything like that. Unless I'm doing like a stencil that requires that I put a lot of pressure, and you know, I've got these callus bumps from years and years of working with tattoo machines and making stencils by hand and that kind of thing. So I will bulk up a pen if I'm going to be doing stencil for that reason. But my thought is that the reason people like a larger grip is because there's weight back here, and so that weight pulling this way, by having a bigger grip here, you're creating more leverage and less of a pressure point for the purpose of eliminating this kind of thing on your finger. However, because the motor is here in this unit, so the bulk of the weight is actually in your hand. And even, and especially if you're using a stainless grip, then the weight is even lower. So these side by side, the balance point of this one is roughly here. The balance point of this one is roughly here. So by having a stainless, your center of gravity is even lower. So there isn't a need for leverage as much as what we're used to with a rotary that has weight, or even any tattoo machine that has weight back here. Particularly a coil, which I would say is one of the bigger downsides of a coil, is that having all that weight back here, that, you know, then you want to grow a big fat grip because the leverage is used to offset that. But because all the weight is in your hand, that's my thinking on that, is that you don't really need to have a big fat grip. I will be making, in fact, I'm making some right now, and I have some prototypes here. Use your imagination on this one. This is 3D printed, and we ran out of black material, so we finished with white. But this actually is functional, and I have tattooed with it, and I enjoy it. I'm going to work with it some more before I really make my determination, but having that big fat grip in the front, it actually does feel nice. So I'm starting to wonder if maybe it's just a preference thing. To me, this still is my preferred one, the stainless particularly. It feels really solid, and I don't have to put much pressure because the machine weighs a lot. This one is aluminum, and it weighs 4.2 ounces or 120-ish grams, and this one weighs 6 3/4 ounces or around 190 grams. And that's my preferred one at the moment. You know, if I was working 5 days in a row, 8 hours a day on, you know, one client and not having breaks, that might get tiresome. I'm not really sure though, because again, I'm not having to push down to get penetration. The machine is doing most of the work, so I'm just moving it. So I kind of prefer it like that heavy. And actually, you'll notice that this one has a kind of unique grip design here that was actually a mistake, and that's why it's mine. And this is how they will come. So yeah, bigger grips are coming. And as far as disposables go, I'm still kind of crossing that bridge at the moment. I like the idea. I like how clean it is. The thing that I don't like about it is that we're putting more plastic into the landfills. And I know that is, that's an ongoing and increasing concern for the world, that we are, not conscious about the materials that we're using. And so before I get, I don't want to just jump in and make plastic grips, because people like it, and I get it. These can be completely submerged in maticide or otherwise, and it takes a total of 6 minutes to get this completely sterile. If you just to put it in, walk away, it won't ruin the finish. So for now, I'm saying that that's the solution, and disposables are disregarding the concern, in my opinion, that we're putting plastic into the landfills. And to address the recycling solution, it's not a solution. Recycling can only be done once in most cases. In extreme cases, it can be done 2 or 3 times. So while that does reduce the amount of plastic as a whole going into the landfills, it doesn't eliminate it. So I'm looking into other options like, like even bioplastics. It's actually just an additive, and it doesn't eliminate the microplastic concern. There is hemp plastics. Doing some research on that. I'm not sure if that's a solution or not. And there are a couple other materials that I'm looking into. So in other words, I'm at work on it, but I'm not willing to put out something without taking all these things into consideration. And that's about it. I think that other questions people sometimes have is about batteries. They are compatible with all of them. In fact, they're quite compatible. I would say it's a brushed motor. So the brushless motors, a lot of times they have problems with batteries, the use of batteries. They vary. So they work, but the speeds aren't going to be as predictable, whereas a brushed doesn't have that concern, that issue. So I will be getting into that at some point. I just not at the sacrifice of performance. So I'm unwilling to sacrifice the performance for convenience, because I believe that the performance is the more important aspect. So yeah, I think that covers it, and feel free to ask questions. I will consider making more videos like this if I feel that it will answer questions more effectively, which is ultimately the purpose of this video, is to try and get the information across with a more understandable mechanism than just, letters on a page. So thank you for watching, and I'll see you later. Okay, I was watching the video, or editing it together, and noticed there's a couple of things I just wanted to clarify a bit more. So one being that when I was mentioning the weight increase, what I didn't mention is that the reason that the center of gravity is dropped with the stainless, version is that the bulk of the metal in this piece is like from this point from this point down, let's say. And most of this is very thin. It's less than 1 millimeter thick here. So what I'm doing here by adding stainless, because the rest of this is actually still aluminum. So making stainless grip, you're dropping the center of gravity down because there's a big chunk of metal down here. And also, I had pointed out that these are autoclavable. But when I was pointing that out, they were not separate. So I just wanted to clarify that this piece is not autoclavable. And if you autoclave that, it will destroy the motor. So the grip is autoclavable. The cam is also autoclavable. I would recommend only autoclaving the cam if, something happens to it. In other words, if it's contaminated, I would go ahead and autoclave it. But you can also submerge both of the cam and the grip in maticide or similar to cold sterilize. So that's it. That's the last two things I wanted to point out. Thanks again.